Hello everyone, I am Martinez Trivino from University of Granada, and today I will talk about an introduction to Phi3 minimal surfaces in R3. It is a joint work with Antonio Martinez Lopez from University of Granada and João Paulo dos Santos from University of Brasilia. The sketch of this talk is the following. Firstly, I will introduce the family of Phi3 minimal surfaces in R3 from three different points of view. Moreover, I will introduce the definition of stability as locally minimum of a weight area functional, together with some fundamental equation that we will use this equation throughout of this talk. On the other hand, we study the most symmetric examples. We study the existence of phi3 catenary cylinders together with asymptotic behavior. We classify all complete flat phi3 minimal surfaces when phi is a diffeomorphism of R to R. And moreover, we study the example rotationally symmetric, complete rotationally symmetric phi3 minimal surfaces together with asymptotic behavior. In the third section, we will study the mean convex properly embedded phi3 minimal surfaces. We obtain area and curvature estimates and will characterize of the convexity of this family of surfaces as the same way that the Sprung-Chow theorem for translating solitons. Finally, we characterize the example phi3 ball and phi3 catenary cylinder thanks to the asymptotic behavior. Okay, so let's start with the introduction. The equilibrium of a flexible inextensible surface under an external force was described by Poisson. Namely, when the tensions are equal, then Poisson proved that the equilibrium condition is given by the following two equations. Notice that the blue part of the first equation can be written in terms of the mean curvature. On the other hand, the second equation holds if and only if this force is conservative and the potential function coincides with the tension at a constant. From this equation, Poisson obtained the following particular case: the equation of minimal surfaces in R3, the equation of capillary surface, and the equation of a flexible surface under gravitational force phi when the force only depends of or two constants J and rho, and the tension is a linear function which only depends of the third coordinate. In this last case, in a more general way, we can consider external force of gravitational type given by this function E, such that it's a density of sigma which only depends on the Higgs function of the third coordinate. Okay. In this case, the equilibrium condition is given by the following equation, where phi is the smooth function defined as this form. Notice that in this case, the potential of the force is given by the exponential of this phi. Moreover, notice that this equation generalizes the classical minimal equation in R3. On the other hand, equivalently, we can write the previous equation 3 in terms of the mean curvature vector as follows. This equation allows us to introduce the main class of surfaces of this torque. Namely, when phi is a smooth function and sigma be an orientable immersion in R2 cross I, we say that sigma is phi3 minimal if and only if the mean curvature vector satisfies the previous equation 4. Some particular case of this family are the classical translating solid of the mean curvature flow when phi is identity. For example, we obtain the Green Reaper and take the Green Reaper, example invariant some translation in R3, and rotationally symmetric examples like ball and wing light translators. On the other hand, we obtain or we recover the singular and familiar surfaces. This family describes the shape of a hugging roof, which is the important for the construction of perfect domes, according with the works of the architecture Otto and Rafael Lopez from University of Granada. Particular case of this family are example invariant by horizontal translation, like the previous Green Reaper and Title Green Reaper, and rotationally symmetric examples. Notice that the geometry of this surface depends on the sigma alpha. This fact we will present throughout of this talk. Next, I will introduce the invariant space. Let phi be a smooth function. The Riemannian space is the following Riemannian trimanifold whose matrix is a conformal change of the Euclidean metric. In this case, the main curvature of any immersion in the Riemannian space satisfies this blue equation, where h is the mean curvature of the surface with respect to the Euclidean metric and overlying nabla denotes the usual gradient operator in R3. Consequently, a surface sigma in R2 cross I is phi3 minimal if only if it is a minimal surface in the Riemannian space. The property of to be minimal will be present throughout this talk. For example, from a work of Edinburgh, we can recover the classical maximum principle for minimal surfaces in Riemannian trimanifolds. Okay? Now, we'll introduce this family from a variational point of view. Let phi be a smooth function. Denote by nabla and delta the gradient Laplacian operator in sigma and define the following weight area. Function. If x is a variational vector field with compact support, then the formula of the first variation of this area is given by the following expression phi. In particular, if we assume that sigma is orientable, then the previous equation phi is equivalent to this equation 6. Consequently, any phi3 minimal immersion is a critical point of this area functional for any number of variation with compact support. Joining all the information, we obtain the following result. Sigma is a phi3 minimal immersion if only if sigma is a minimal immersion in the Riemannian space. Sigma is a critical point of the previous area functional and the normal for any normal variation with compact support. And sigma is a flexible inextensible immersion in equilibrium on the gravitational type and whose tension forces are equal. Okay? Next, I will introduce the definition of stability. Let sigma be a phi3 minimal immersion without boundary in R2 cross I. If x is a normal variation field determined by a function u with compact support in sigma, then the formula of the second variation of the previous area functional is determined by the following Schrödinger operator defined by the expression h. Notice that this term is the drift Laplacian defined by the equation 9, and this term is the classical Brachy-Emery tensor for the formula of the second variation of area functional for any in an immersion in a arbitrary Riemannian manifold. Okay, in this case is the Euclidean Hessian of phi. From this equation, we will say that an orientable phi3 minimal immersion is stable if only if, for any smooth function with compact support in R2 cross I, the following equality holds. Okay? It's a locally minimum of the previous area function. Now, if we see sigma as minimal immersion in the Riemannian space and denote by J the operator of stability with respect to the Riemannian metric, then Chen, Mejia, and Zhu prove the following equality for any smooth function with compact support. So we obtain that sigma is stable in R2 cross I, according with the previous definition, if only if sigma is stable in the Riemannian space as minimal surface in this space. Next, I will introduce some fundamental results that I will use the result along of this talk. The node by T be an phi3 minimal immersion whose Gauss map is M. The node by Xi eta sub I, the coordinates are angle function respectively of sigma, okay? In this case, the mean curvature can be written as follows. So this function satisfies an elliptic partial differential equation of second order. And so from the Hopf maximum principle, we obtain the following results. Okay, let phi be an strictly increasing convex smooth function and consider sigma be phi3 minimal immersion with negative mean curvature. If there is an interior point in some of this open set where this quotient attain a local maximum, respectively a local minimum, then this function must be a constant over the surface. On the other hand, we obtain a maximum principal from the mean curvature. Namely, when phi is a diffeomorphism such that satisfies this inequality for some lambda positive, notice that when phi is a convex, this inequality is trivial. And consider sigma be a phi3 minimal immersion in R2 cross this interval. Mean convex, in this talk, mean convex means that mean curvature is non-positive. Then we obtain that if the mean curvature vanishes anywhere, then the mean curvature vanishes everywhere, and then sigma is an open subset of a vertical plane. On the other hand, thanks to a Hamilton maximum principle, and together with a result of Saba, Halila, and Smolsky, we recover a maximum principle for the Gauss curvature. Namely, when phi is a strictly increasing smooth function when the third derivative is not positive, and consider sigma a locally convex phi3 minimal immersion, then we obtain that if the Gauss curvature vanishes anywhere, then sigma must be flat. Next, we study the most symmetrical example. Firstly, we study vertical graphs invariant by horizontal translations. Consider a vertical phi3 minimal graph given by a function which only depends on one variable. Bear in mind the equation of phi3 minimal graphs. This function U satisfies the following equation 10. To look for complete example, we will consider that phi is a diffeomorphism. Then, in this condition, we can take the following change of variable, and we obtain that the previous equation takes equivalent to the following system 11, whose diagram of phases is given by the following picture. A consequence of this diagram is the following. Fix an orbit in this picture, then there exists a unique real number such that the tangent is 0. Taking this initial condition, we have that for any real number non-negative, the solution U is given by the following expression. Joining all the properties of this solution, we obtain the following two theorems. Namely, we consider phi a diffeomorphism strictly increasing. In this case, the solution U is convex even and has a minimum in the origin. Moreover, if C is finite, then this solution U is defined over R, and this solution tends to infinity with the following asymptotic behavior. On the other hand, if C is equal to infinity, this function tends to infinity and is asymptotic to two vertical planes, infinite time or infinity time. Well, in fact, this solution is defined over a bound interval if and only if this potential, this exponential, is integrable. Now we consider phi. This condition, for example, we obtain we recover the classical ring reaper translated soliton, such which is asymptotic to two vertical planes in the points p over 2 minus p over 2. On the other hand, suppose that phi is a strictly decreasing diffeomorphism. In this case, U is concave even has a maximum in the origin. Moreover, if C is finite, then this function is defined over a bound interval and cuts the plane theta equal to A with this inclination, or with this asymptotic behavior. Okay. On the other hand, if C is equal to infinity, we recover the previous result, that namely this function U is defined over a bound interval if only if this exponential is integrable, and moreover, this function U cuts orthogonally the planes Z equal to A. The cylinder associated to this function U will be called phi3 catenary cylinder. Now, if we consider a phi3 catenary cylinder and apply a rotation of angle theta above the x-axis and apply an amorphity factor 1 over cosine of theta, the resulting surface is also phi3 minimal, and we are going to refer this example as theta phi3 catenary cylinder. Surprisingly, this example, together with the vertical plane, are the only incomplete flat phi3 minimal surfaces when phi is at the diffeomorphism of R to R. The main idea is the following. Because sigma is a flat, consider n be a straight line containing sigma and denoted by n sub n, the unit normal vector and length of this point. If all the angle function vanishes, then sigma is a vertical plane. On the other hand, when the angle function is not zero, then because phi is a diffeomorphism of R to R, and bear in mind the diagram of phases, then we can obtain an initial condition such that the phi3 catenary cylinder associated to this initial condition contain the straight line L, and it is tangent to the surface and log on these points. The uniqueness, the proof follows from the uniqueness of the previous Cauchy problem. As a consequence of this classification, we obtain that the following corollary. If we assume that the third derivative of phi is non-positive and consider sigma a complete locally convex phi3 minimal immersion, bear in mind the maximum principle by the Gauss curvature, we get that the Gauss curvature vanishes anywhere, then the Gauss curvature must be constant zero, and so sigma, using the previous theorem, sigma must be a vertical plane or a phi3 catenary cylinder may be taken. Now we study the rotationally symmetric phi3 minimal immersion. In this case, the equation of phi3 minimal graphs is determined by the equation 12. Notice that this equation is degenerated in the origin, so the system is not guaranteed by classical theory of ordinary differential equation. However, Schoring proved that a continuous solution of the phi3 minimal graphs has no isolated singularity. Consequently, it is not a characterization to study the system of solution with the following initial condition. However, as a consequence of the Banach-Fischer point theorem, we can guarantee locally the system of a unique solution U of the previous Cauchy problem. Okay, so if we extend this solution using the classical prolongation theory of solution, we obtain the following two results. Let phi be an strictly increasing convex Morse function. Then there exists a complete globally convex rotationally symmetric graph defined over this center in the origin of radius R, such that this solution has a global minimum in the origin, and this solution tends to infinity in the boundary of this disk. This example will be called phi3 Bors. On the other hand, when the initial conditions are outside of the origin, we obtain the following result. Let phi be an strictly increasing convex Morse function. There exists a complete embedded rotational phi3 minimal surface with the annulus topology and whose generating curve is of the wing light type. This example will be called phi3 minimal catenoids. Surprisingly, the cylindrical asymptotic behavior only depends on the polynomial growth of phi. Namely, when these functions are not cylindrically bounds, when phi has as much quadratic growth. On the other hand, these solutions are cylindrically bounds. Motivated by this result, we study the asymptotic behavior of rotationally symmetric examples when phi is a strictly increasing convex Morse function, like the previous result, but we need to assume the following expansion in the infinity. In this case, alpha is non-negative and beta is positive when alpha is equal to 0. Okay? For the particular case of translating soliton, Clutterberg, Schnurre, and Schur describe the asymptotic behavior of rotationally symmetric translating solitons. Namely, when the radius tends to infinity, the translating soliton has the following the translating soliton have the following asymptotic behavior. In our case, we obtain the following result. If alpha is positive, then this function phi has the following smooth function. Because phi is strictly monotone, we can recover an asymptotic behavior for the function smooth, for the function u. Okay. On the other hand, if alpha is equal to 0, then up to a constant, this function given by this expression, notice that this function is again strictly monotone. Then we have the following smooth, we have the following asymptotic behavior. Notice that this case is coincide with the previous case of translating soliton when the first derivative coincide with beta coincide with 1. Okay, we recover the previous result of Clutterberg, Schnurre, and Schur. Okay, so let's start with the third section where I will study the global geometry of mean convex properly embedded phi3 minimal surface. Motivated by the following words of Brian White and Schoen for a stable minimal surface in R3, Rosenberg, Swan, and Tubiana for a stable CMC surfaces, namely constant mean curvature, in 3 manifolds with boundary geometry, and the work of Sprague-Chow for mean convex translating soliton in R3, in this section, we establish area and curvature estimates for this family of surfaces when phi is a strictly increasing convex function. Moreover, we characterize the convexity of this family when phi has a quadratic row and the third derivative is non-positive. Okay? Firstly, first a stable example. Notice that the system of a stable example is not guaranteed. For example, from a work of Chen, Mejia, and Zhu, Chen, Mejia, and Zhu proved that if the function phi is less or equal to a negative constant, then there are not a stable example when finite area. Okay. On the other hand, Spinner proved that when phi is less or equal to a negative constant, and the surface has finite phi capacity, then the only stable example is the vertical plane, because must be totally geodesic. Okay. However, under our condition, we can guarantee that any complete mean convex phi3 minimal surface is stable. This result justifies the previous hypothesis. On the other hand, if U is a vector field such that is orthogonal to the vertical direction, then any horizontal graph or a graph with respect to the vertical with respect to the Killing vector U, then sigma is stable for any function. Sigma is stable for any function phi. Okay, so if we joining this result together with the work of Chen, Mejia, and Zhu, we prove that there are not vertical graphs with finite weighted area. Next, consider phi be an strictly increasing convex smooth function satisfy the following inequality. Notice that when phi has a quadratic root, this inequality is trivial. Following the method of Sprague-Chow together with a Kligenberg argument, we can establish the following area bounds. Under an assumption, if we fix for any fixed point P of sigma and consider a radius rho satisfying both inequality, then the geodesic disk centering P or radius rho is disjoint to the code locus of P, and we obtain the following area estimates. Notice that we need to assume this hypothesis because spiritual using a result of coordinate for a surface with bound mean curvature. But in our case, we cannot guarantee that the mean curvature must be bound. Okay, it is the first resort. Now we study the blow up and the curvature estimates. We establish a curvature bound for mean convex properly embedded orientable phi3 minimal surface with locally bounded genus. Moreover, we need to assume that phi is a steadily increasing convex with the following asymptotic behavior. It is this curvature estimate is a consequence of a blow up result. We see this result in the following slides. As corollary of a compactness result of Bryant White for minimal surface with locally bounded genus. Okay, so we need to assume this hypothesis in topology. Our Brouwer result say us the following: if lambda n is a divergent sequence of real numbers, Pn is a sequence of points such that satisfy this limit, then the sequence of blow up of the surface smoothly converge to the following some case. Converge to a minimal plane if C is equal to 0, or the following or one of the following case translating soliton if C is positive. Which is the catch of the proof? Okay. Firstly, notice that each sigma n can be seen as minimal surface in the corresponding immanent space. Moreover, in compact subset, we can guarantee that this sequence of function smoothly converge to this function. On the other hand, the area is locally uniformly bounded from a monotonicity formula for minimal surfaces in Riemannian thin manifolds of Bryant White. Okay, so up to subsequence, we get that this sequence converge smoothly to either a minimal surface if C is equal to 0 or a translating soliton if C is positive. Firstly, if C equal to 0, we get that the limit is complete stable minimal surface in R3. Consequently, the limit must be a plane. On the other hand, if C is positive, we obtain that the limit is a complete mean convex translating soliton. Using the exact state theorem, we obtain that sigma is either a vertical plane or a graph. In the second case, if the limit is a graph, we obtain that the limit is a complete translating soliton graph. So the proof follows using the classification of Hoffman, Ilmanen, Martin, and White. Okay, so as a consequence, we obtain the following theorem. It is our second result. Let sigma be a mean convex properly embedded phi3 minimal surface with locally bounded genus, and phi satisfying the previous condition. Okay, then this theorem assures us that this quotient is bounded in sigma. Notice that if the first derivative of phi is bound, then the second fundamental form is bound in sigma. For example, the case of the particular case of translating solitons. Which is the catch of the proof? Okay, so we argue by contradiction. Suppose that there is a sequence of points such that the limits tend to infinity. Consider the sequence of blow up of the surface when lambda n is given by this divergent sequence of real numbers. Okay, from the previous blow up result, we get that sigma n smoothly converge to a plane in R3, but by definition, the limit is not totally geodesic, but it is a contradiction because the limit is a plane. Okay, this is the catch of the proof. Now we get a characterization of the convexity of this family of surfaces. Bear in mind the spiritual result, he proved that any mean convex complete translating solid in R3 is convex. Moreover, this result solves the one conjecture. So joining both results, we can assure that the only entire translating soliton graph is the ball translating solitons. Here, we can characterize the convexity of the mean convex properly embedded when phi is a strictly increasing convex smooth function when this function has at most quadratic growth and the third derivative of phi is non-positive. The main tool of this result is a Omori-Yau maximum principle for the drift Laplacian. In the classical theory, the Omori-Yau maximum principle appears to for the classical Laplacian. In ambient space with sectional curvature is bounded from below. On the other hand, the classical Omori-Yau principle for the Laplacian had been applied for complete surface. However, in our condition, cannot assure the completeness of sigma and the Omori-Yau maximum principle holds in our family of surfaces. Okay, however, under assumption as above, any properly embedded phi3 minimal surface in R3 is complete, and moreover, the Omori-Yau maximum principle for the drift Laplacian holds. Which is the catch of the proof of this lemma? Up to horizontal translation, we can assume that the origin is not contained in sigma. So, okay, consider gamma the following as a most function given by this expression. Because sigma is a properly embedded, this function tends to infinity for any divergent sequence of points in the sigma. On the other hand, for the quadratic growth of phi, the following Kac-Minsky conditions hold. Namely, there exists a constant C positive such that the gradient drift Laplacian is bound. Are bound. Consequently, from a work of Louis Alias, Mastriola, and Rigoli, the Omori-Yau maximum principle holds for the drift Laplacian, and taking any divergent geodesy or any divergent curve, then the curve has infinite length. This property, this property proves the completeness of this family of surfaces. Okay, our result of characterization of the convexity is the following theory. Let sigma be a mean convex properly embedded phi3 minimal surface with locally bounded genus. Okay, and consider phi and a smooth function satisfying the previous condition. Then the Gauss curvature k is non-negative if only if this function is bounded from below. Notice that for the particular case of translating soliton, alpha is equal to 0. So we recover the Sprue-Chow theorem. As a consequence, we obtain the following two results. Suppose that this function is bounded from below. If this sequence is a divergent sequence of points, and lambda n is a sequence of real numbers such that this limit holds for a positive constant, then after passing to passing to subsequency, this sequence of blow up of sigma smoothly convert to smoothly convert to a complete flat translating soliton. So either this limit is either a vertical plane or a green reaper translating soliton may be tilted. On the other hand, if we assume that this function is bounded from below and bear in mind the maximum principle by the Gauss curvature, if k vanishes anywhere, then sigma is flat. Okay, so let's start with the last part of this talk. We characterize the sample theater board and phi3 catenary cylinders by their asymptotic behavior. Firstly, we study the uniqueness of the phi3 boards. Bear in mind the two sections of this talk. We study the system And the asymptotic behavior of this example when phi is a strictly increasing convex smooth function with a most quadratic group. Okay, so under this condition, the goal is to characterize the example phi3 ball from its asymptotic behavior. Recall that the asymptotic behavior of rotationally symmetric phi3 minimal surface satisfy the following equation. The following equation depends of the value of alpha. The main tool of this proof is the method of Alexandrov for vertical planes. Notice that this coordinate is equal to t when for u and horizontal. Where u is a horizontal vector. Okay, so we introduce some notation. We denote by pt a vertical plane. Sigma plus and sigma minus denotes the right part and left part respectively with respect to the vertical plane. Sigma star is the reflection of sigma with respect to the vertical plane. And we say that this set is in the right part or is greater or equal to this set if and only if the first coordinate of this point, the infimum of the first coordinate of this point is greater or equal to the first coordinate of this point. Okay. With this notation, we'll introduce the definition of smoothly asymptotic. Let sigma be an embedded phi3 minimal surface with a single edge. We will say that sigma is smoothly asymptotic to a phi3 ball if the residual radius large enough such that the surface outside a Euclidean ball centering the origin and radius r can be written as a vertical graph satisfying the previous asymptotic behaviors. As a consequence of this asymptotic behavior, the following properties holds. Namely, there exists a radius large enough such that the right part of sigma is a graph over the vertical plane pt. On the other hand, for any t larger enough, we can find an epsilon positive, small enough, but there exists a positive epsilon, such that the reflected graph is over with respect to the graph u. Consequently, from this property, we can start the Alexandrov method and prove that our surface is symmetric with respect to any vertical plane. Consequently, we obtain our uniqueness results. Namely, when sigma is a complete properly embedded phi3 minimal surface in R3 with a single end which is smoothly asymptotic to a phi3 ball, using the previous slides, we get that sigma is rotationally symmetric, and the proof and the result follow using the uniqueness of the phi3 balls. Okay. Finally, we study the uniqueness of the phi3 catenary cylinders by their asymptotic behavior. For the particular case of translating soliton, Martin, Perez, Savage, and Smolkin proved that a connected properly embedded translating soliton in R3 with locally bounded genus, which is closer in C1 topology to two vertical planes, two planes outside a cylinder, then this translating soliton must be coincide either a vertical plane when the two planes coincide, or a Green Reaper cylinder. In our case, we will prove the following theorem. Let phi be an strictly increasing convex diffeomorphism such that this potential is integrable and this quotient is bounded. If sigma is a connected complete phi3 minimal graph which is C infinity asymptotic to a phi3 catenary cylinder outside a horizontal cylinder, then sigma coincides with some phi3 catenary cylinder with the same asymptotic behavior that the previous catenary J. Okay? Justifying the hypothesis. Firstly, we record that we give the system of complete phi3 catenary cylinders when phi is strictly increasing diffeomorphisms which are asymptotic to two vertical planes when this exponential is integrable. We see this property in the section number 2 of this talk. Yes, number 2. On the other hand, we give the system of complete convex phi3 balls when phi is strictly increasing convex, and moreover, we study the asymptotic behavior of this example when phi has at most quadratic growth. Finally, the main idea of the proof is to show that the angle function eta2 is, that is, the angle function with respect to the horizontal direction E2 vanish everywhere. In such case, if sigma is a vertical graph, then sigma is invariant by horizontal translation in this direction. So from the asymptotic behavior, this surface, it must be coincide with some phi3 catenary cylinder with the same asymptotic behavior. Okay. Definition. We say that sigma is ck asymptotic to a phi3 catenary cylinder outside a cylinder if there exists a horizontal solid cylinder C whose axis coincide with the axis of the phi3 catenary, and the two connected components of sigma outside of the cylinder, sigma 1 and sigma 2, are ck asymptotic to the right part of the phi3 catenary cylinder and the left part of the catenary cylinder, respectively. Namely, they can be parameterized as a graph over the catenary by a function over line U of class ck such that this function tends to 0 in ck topology. Recall that the main goal of this theorem is to prove that the angle function eta2 is equal to 0. Okay, so we need a control in the infinity of this direction. This theorem shows us the following property. Suppose that Bn a divariant sequence f of real number and consider the horizontal translation of sigma. Then after passing to up to sequences, these sequences converge smoothly to a properly embedded connected phi3 minimal, which has the same asymptotic behavior as sigma. Which is the sketch of the proof. Okay, the node by set the blow up, the points of blow up of area. If we show that this set is empty, then this sequence has locally uniformly bounded area. So we can apply the compactness result of Bryan White to assure the system of limit. Okay. So, okay, we argue by contradiction. Assume that this set is not empty. Firstly, from asymptotic behavior, we can assure that we can prove that this set is contained in the cylinder C. Now, because phi is a strictly increasing convex smooth function with quadratic growth, we can find a first phi3 ball outside of cylinder. Now, if we translate in the direction minus E3, we can find a phi3 balls with another phi. Recall that the vertical translation is not isometry of all class of surfaces. Okay, so we obtain a phi3 with another phi. Okay, balls such that it has a first point of contact with the set. Okay, so from a strong variant principle, Bryan White, such that this set of points satisfying is like a classical maximum principle for minimal surfaces. We show that this ball, okay, must be contained in the horizontal cylinder, but it is a contradiction because this ball tends to infinity when the radius tends to infinity. Okay, so it is a contradiction, and this is empty. So we can apply the compactness result of Brian White to guarantee the system of limit. Finally, we finish this talk proving the uniqueness of the phi3 catenary cylinder by their asymptotic behavior. Okay. Firstly, from the maximum principle for the mean curvature, we can assume that the angle function is positive. On the other hand, consider a compactness auction whose boundary consists in 4 curves. From the previous result in the previous slides and the asymptotic behavior of sigma, we can prove that for any epsilon positive, for any positive epsilon, there exists an integer larger enough such that for any integer greater or equal to n0, we get that the following inequality. Notice that from this inequality, this quotient tends to 0 for any divergent sequence of points of sigma. Consequently, by completeness, this the function eta 2 over eta 3 reach either an integer maximum in this open subset or an integer minimum in this open subset. Notice that these sets are not empty. Otherwise, if one of these sets is empty, our surface must be a multigraph in the direction E2, but it is a contradiction due to the asymptotic behavior to the phi3 catenary cylinder. Okay, so finally, from the convexity of phi, together with the strong maximum principle of eta 2 over eta 3, we had seen the result in the first section of this talk. We proved that this quotient is constant. Okay, but this quotient tends to 0 and infinity. So this function is constant to 0, and the angle function eta 2 vanishes everywhere as we want. Okay, so the main bibliography of these results is the following. It's joint works with João dos Santos from University of Brasilia and Antonio Martinez Lopez from my advisor from University of Granada. And it is all. Thank you so much for your attention, and thank you so much for your invitation. Bye-bye.